Resources Division. Welcome everybody to, we're getting a lot of feedback, so if everybody could put your phones on mute, please, that would be very helpful. Welcome to session 4 of the TDep white.
I'm going to talk to you about a chapter in the TDep white paper today that deals with exploring the use of low-cost methods for routinely monitoring air surface exchange of reactive nitrogen compounds. So low-cost methods for dry deposition measurements, essentially. I'll be talking about the work today, but I have Ryan Daly here. He's with me at EPA, and he's been really leading the development of the hardware and software of the system that we're going to discuss with you today. And Kathy Berry and Marcus Stewart at Wood, I believe they're on the line. They're helping us develop some of the SOPs for this work. So what's the motivation for exploring these low-cost dry deposition measurement systems? Well, we know that dry deposition is an important part of total deposition, and in many cases exceeds the wet deposition component. We also know that dry deposition is more difficult to measure than wet deposition, and so there's a lot less data on dry deposition for assessing that component of the total budget and for developing and evaluating dry deposition models. So we really need more long-term measurements of speciated dry deposition for characterizing temporal and spatial patterns of dry deposition at seasonal to annual time scales and regional to national spatial scales. And again, we need these data sets to improve dry deposition models to reduce uncertainty in assessments of total deposition budgets. For example, the TDep approach that we're all familiar with. And deployment of continuous measurement systems for traditional microbiological flux measurements at a large number of sites is really cost prohibitive. Typically, these systems that measure one or a couple of compounds in a continuous 30-minute or hourly mode are quite expensive, 50K or more than 100K. And so thinking about deploying a large number of these systems at a single site to measure the entire speciated dry deposition budget, and then doing this at a lot of different sites to characterize spatial variability is really not practical. So what we're talking about today is the use of low cost, and when I say low cost for a flux measurement system, I'm talking about something maybe on the order of 20K, methods that are suitable for measuring dry deposition in a routine monitoring mode. These are the types of systems that we need to really get out there and assess spatial and temporal variability for developing budgets. So what would chemical flux measurements in a network mode look like? Well, the idea here would be to optimize the network for spatial coverage. The objective is really to develop deposition budgets on seasonal or longer time scales, not really to examine the flux processes in detail like you would with the more expensive measurement systems that are allowing you to measure processes on a 30-minute time scale. We're talking about integrating over time and looking more at total budgets on seasonal or annual time scales, and really getting at spatial and temporal variability. But we want to use a flux approach that's physically sound, so ideally we're going to use a micrometeorological type flux measurement method. Another key here is that we need information on a suite of different compounds for reactive nitrogen, not just one analyte. So we would like to measure multiple analytes in the gas phase, nitric acid, ammonia, for example, and in the particle phase with one measurement system. Again, to deploy these things at lots of different sites, we need for the cost to be relatively low for an individual system. They must be suitable for routine unattended operation. And really, we're talking about using time-integrated sampling techniques like denuders and filter packs. And there's a precedent for the use of these time-integrated approaches like filter packs with CastNet and the improved networks and other monitoring networks. So a couple of key concepts here for the type of approach that we're going to talk about today. And one is the concept of integrating the atmospheric measurements over time. I'm showing you a basic schematic here that sort of illustrates the basic basic concept here of using a traditional micrometeorological gradient method to directly measure the flux. So I'm showing you here a little picture of a cartoon of a forest, and above this forest you can imagine that there's a concentration gradient of some compound C with higher concentrations well above the surface, and then a concentration gradient decreasing toward the forest canopy. We want to measure this concentration gradient, and that's going to be, our flux is going to be proportional to the concentration gradient. So the gradient approach requires you to measure the concentration of whatever you're interested in at least 2 heights above the surface, and then the micrometeorological parameters that allow you to calculate the flux rate, the mass transfer per area per unit time, using your measured concentration gradient. In this case, though, instead of measuring the gradients on a 30-minute or an hourly time step as you normally would do, we're going to sample the gradients over extended periods of time from 1 to up to 4 weeks. So that's the concept of a time-integrated gradient measurement. And the system that we're going to talk to you about today is kind of a variation on an original, what was coined a conditional time average gradient system that was developed for sulfur dioxide and ammonia by Daniela Familari and her colleagues at the Center for Ecology and Hydrology in Scotland. They developed the first system and really pursued this concept. And then what we're going to talk about today is a system that we're working with here that's based on that original design, but with some modifications. And these COTAG systems have been used throughout Europe, for example, during the Nitro Europe study. And if you want to read up a little bit more about the technique, I have a reference here that you can follow. So another key concept here is this idea of conditional sampling. And we employ conditional sampling so that we can meet some of the requirements of the micrometeorological gradient methods. And what here I'm showing you here is kind of a simple example that illustrates how the measured gradients can relate to different stability regimes. And so this idea of conditional sampling is to sample only during discrete periods of stability and then calculating the fluxes for those different stability conditions. And so that's another concept that underlies this conditional time average gradient approach, is that we're going to only measure the concentration gradients during specific stability conditions that meet the requirements of the micrometeorological gradient technique. So here's a little bit of math. I just wanted to put these up here for those that are interested in the theory behind the flux calculations. Using gradient measurements, you can calculate fluxes in a couple of different ways. The traditional method on the left-hand side is the aerodynamic gradient method. The flux of some compound is equal to its turbulent eddy diffusivity applied to the vertical concentration gradient. And you can do some rearranging, and using the traditional approach, you can calculate the flux by employing these empirical stability functions. This is a pretty straightforward way to go, but it works best when the atmosphere is well mixed and is in this near neutral condition. These stability functions become quite large. The correction that they contribute to the flux calculation really becomes quite large for very non-neutral conditions. So if the atmosphere is highly stable at night or very unstable during the day, these corrections become quite large. And so that's another reason why we want to set specific windows for these stability conditions under which we're measuring the gradient. There's an alternative approach called the modified Bowen ratio method, which is a little bit more straightforward. It's still assuming that the transfer of mass, so trace gases and particles, is similar in theory to the turbulent transport of heat. So we're calculating the flux by directly measuring the turbulent eddy diffusivity for heat, by measuring the sensible heat flux with our sonic anemometer and the temperature gradient above the surface, using those measurements to directly calculate KH, and then applying that to our concentration gradient measurement. So this approach doesn't require the stability functions, but it becomes uncertain when the heat flux and the temperature gradient become small. So those would be transition periods, say in the morning or in the evening, when the direction of the heat flux and the temperature gradient are changing and therefore become quite small. But what we're proposing is that maybe we can use a combination of these two approaches to extend the temporal coverage of our conditional gradient sampling. So what does this conditional sampler look like? Here's a schematic that shows a configuration for the system that we have assembled here at EPA. And I'll try to tie together some of the details that we've talked about so far. We have 4 gradient sample boxes. We have duplicate boxes at each of 2 heights. So these are the gray rectangles there. And they're only showing 3 channels in the schematic, but we actually use 4 channels. And so these are the channels that define the stability conditions under which we're sampling the gradient. So one channel only samples when the atmosphere is neutral. One channel samples under unstable conditions, which primarily occur during the day. A third channel samples when the atmosphere is stable at night and not extremely stable, but only slightly stable. So we're sampling a range of stable conditions where the stability corrections that I mentioned do not become extremely large. And then a dead band where we may not be meeting these other stability conditions, but we still want to at least measure the air concentration. So while our fluxes may not cover the entire sampling period of a week or 2 weeks or a month, we at least have a continuous measure of the air concentration along with our flux calculations during these different conditions. Along with the sample boxes themselves, we have to have a sonic anemometer to measure the different aspects of turbulence that we need to calculate the flux, including momentum flux and heat flux. So the sonic anemometer really is a core piece of this system as well. And then the package includes some of the other measurements that we need, like the vertical temperature gradient, and the measurements that we need to interpret the fluxes, relative humidity, is the surface wet or dry, etc. So that's kind of what the system looks like that we've developed here. And here's a picture of the system deployed in a sagebrush field in southern Idaho, where we just, Ryan was out there a couple of weeks ago, and he had high winds, snow, and rain. And then I went out and relieved him last week, and I had 50 degrees and sunny conditions, and it was much more pleasant for me. I kind of got lucky on that switch off. But here's what the system looks like in a giant sagebrush field. And you can see the upper and lower sample boxes. So these are the boxes that contain the sampling devices onto which we collect the gases and aerosols to quantify the concentration gradient. We have a control box there on the ground that has a data logger in it that is collecting the micrometeorological information and then using that to tell the valves in the sample boxes which channel to sample. You can also see the aspirated thermocouples there that we use to calculate the temperature gradient. And off to the side, you can't see it, but we have a short mast where we're measuring solar radiation, rainfall, surface wetness, and we have some sensors in the ground for soil temperature and soil moisture. But that's what the gradient system looks like as deployed currently in the field. So let's talk a little bit about the sampling aspect of the system for the chemistry. We're using an approach that has been used in the UK acid, gas, and aerosol network. And this sampling approach was also developed by the Center for Ecology and Hydrology in Edinburgh, and it's called the denuder for long-term atmospheric sampling, the Delta denuder. And it consists of a short glass denuder and a filter pack. And the method was developed there for measuring ammonia, nitric acid, nitrous acid, SO2, hydrochloric acid, and speciated inorganic particles, so ammonium, nitrate, sulfate. And as it's deployed in the UK, it uses a low flow rate, so about 320 cubic centimeters per minute, and it's deployed for a month at a time. So this denuder filter pack system samples for a month. They are taken back to the lab and extracted, and this network gives them air concentrations of a monthly integrated time step. And so we're using the same denuders and filter packs, only we're deploying them in a gradient mode to measure the flux instead of just measuring the air concentration. And if you're interested in learning more about these methods or the UK network that employs these methods, I have a website for you here where you can look into some more information. So what do the samplers look like? As I said, they're designed for long-term time-integrated sampling. The systems are small, consisting of a single-bore glass denuder, either 10 or 15 centimeters in length. The denuder is coated with something like phosphorus acid to collect ammonia, or sodium carbonate to collect nitric acid, or you can coat it with whatever you like that will collect the gas that you're interested in. So there's some flexibility there. It employs a three-stage filter pack that, again, you can configure to whatever particulate species you're interested in. So maybe that's a Teflon filter for collection of ammonium nitrate and ammonium sulfate, and a backup filter to collect the nitrate that might volatilize off the primary filter. So you can configure the filter pack however you like. The ruler there gives you some idea of how small these devices actually are. And then on the right-hand side, this is a look at the inside of one of our sampling boxes. There at the inlet, there's a short piece of Teflon, followed by two denuders that are used to collect ammonia. So these are acid-coated denuders, a primary denuder, and then a second denuder in series to collect any breakthrough that might occur. And then two more denuders that are coated with a base for collection of nitric acid, SO2, et cetera. And again, a backup denuder is employed there, followed by the filter pack. So that's what the system looks like deployed in the field, with a rain shield over the two denuders that extend below the sample box itself. So I wanted to talk to you a little bit about the flow system, because here's the aspect of the system where low cost comes into play. This is a look at one of the sample boxes, the inside of the sample box, below the plate in front of which the denuders and the filter packs are located. One of the key aspects of this system is that we control the flow rate, which is very low, again, designed for time integrations of a week or more. Flow rate is about 300 cc's per minute, and we control the flow using a critical orifice type system. This is much cheaper than putting a $3,000 mass flow controller into each box. So the way this system is designed is that we measure the pressure in the airstream upstream of the critical orifice, and then you can see the channels that control the opening and closing of the the valves that open and close the four different channels, so that we can sample onto one channel at any given time. Then you have your critical orifice there, and then we have another pressure measurement downstream of the critical orifice. And the orifice is designed to achieve a certain flow rate. And as long as we keep the ratio of the pressure downstream of the critical orifice to about half of the pressure at the inlet, then we can maintain this critical flow that the orifice is designed for. And in this case, that's about 300 cc's per minute. So we also know that the flow through the orifice is a function of temperature. So we measure the temperature of the critical orifice continuously, and so we can calculate the flow rate through the orifice. Now, for this prototype system, in one of the boxes, we do have a mass flow controller, just so that we can confirm that when we measure the temperature of the orifice and we correct the flow rate, that we do get a flow rate that matches what a mass flow controller would measure. That's not a feature that you would necessarily have to employ in systems that were deployed in part of a network, but for this prototype, we have a few more bells and whistles that let us characterize the QA/QC of the system. So that's a description of the measurement system that we've put together at EPA that, again, is based fundamentally on the systems that were developed previously in Europe. And so here's where we are in this work, completed as of this month. Initial work went into developing the SOPs for extracting the denuders and filter packs. We had to develop a quality assurance plan for the scoping study that was conducted in Idaho last fall, and that is ongoing right now. We have completed, I say we, Ryan is doing most of this work. The hardware for the system is all put together and complete, the sampling boxes, the flow system, the micrometeorological components, as well as the data acquisition and control for monitoring the flow conditions, switching the valves based on the communication of the micrometeorology with the sample boxes, et cetera. Those basic aspects of the system are completed. There are some aspects that are ongoing, including the development of the field SOPs for our prototype system. We're improving the QA/QC of the online micrometeorological measurements. So we're tweaking the code to improve some of these aspects, including streamlining of the flow check procedures. So while we're monitoring the pressures on the critical orifice system and monitoring the flow rates in real time, part of the QA/QC is that when you go to exchange these samplers every week or 2 weeks, you directly measure the flows at the inlet with a mistraceable flow meter or flow device so that you can, again, double check the flow rates, because knowing the total volumes sampled during the deployment period is obviously a critical piece of information that you need to know. So we're doing some work there. The system is currently deployed back in Idaho in collaboration with one of our USDA collaborators, April Latham. She's in the Agricultural Research Service. And we're analyzing preliminary data from our fall experiment. And while we're looking through that data more closely now, a couple of things that I can share with you is that the precision of the gradient measurements was sufficient so that we were able to resolve the deposition gradients in all of our samples during the first intensive. And so I think that's encouraging that we can see there at that site, at least, that we have the precision of the chemistry measurements to resolve the gradients. There's also quite a bit of ammonia at that site. In some of our samples, we were measuring 10 or more micrograms per meter cubed of ammonia. And at least in the first study, we didn't see breakthrough on the primary denuder. That's also encouraging. Now, these were shorter deployments of 48 to 72 hours, shorter than we would normally deploy this system, but we were only out there for a few weeks and we wanted to get as many measurements as we could, so we used a shorter sampling duration. But at those higher concentrations, we didn't see any breakthrough. So I'm hoping to be able to share, I'm planning to be able to share more of those results with you for those of you that attend the spring and ADP meeting, but an encouraging first outing for the system, I think. So what would deployment into an existing network eventually look like? Well, there will be some important site requirements. This version of the system that we've put together here runs on AC power. It's possible that we could develop a version of the system that could run on solar power, but for now we are working with the AC power because again, we've added a couple things into this system like the mass flow controller that require a little bit more power, but it is feasible that we could develop a system that runs on solar. We're working with denuders and filter packs, so you need a site operator to change out these samplers. This is a flux measurement, so the site requirements are different than just an atmospheric concentration measurement. To satisfy the micrometeorological requirements, you need a suitable fetch at the site, and that means that you need a somewhat flat, homogeneous surface to an upwind distance of approximately 100 times whatever your sampling height is. So if we're measuring 2 meters above the sagegrass field, then we need an upwind fetch of 200 meters where the vegetation is homogeneous and the surface is flat. So that's a pretty strict site requirement when you compare that to site requirements for just a concentration measurement. So we're not going to be able to do this at every site in the CASNet network or the NTN network or AMON network, for example. So there are some important site considerations. The performance of the system may to some extent be site specific. We're using a micrometeorological gradient technique, and so we will satisfy the micromet conditions more at some sites and less frequently at other sites. For example, where at sites where the winds are fairly light, like some of our sites here in North Carolina, particularly during the summer, we'll have large concentration gradients above the surface that are easy to quantify, but less data coverage due to failure of the stability requirements for nighttime conditions, for example. At sites like our Idaho site that are much windier and rougher, we're satisfying the neutral stability condition more of the time, so it's a good site for conditional sampling. But because the atmosphere is so well mixed because of the wind, the concentration gradients are smaller and more challenging to quantify. And these may be sites where we have to leave the samples out for a longer time period, maybe up to a monthly time step. So there are some considerations for where we will put these systems and how they will perform at different sites. So future work, at least with the system that we're developing here, we will continue developing the field SOPs and other SOPs and continue analyzing the system performance, the chemistry, the precision of the gradient measurements, the flow behavior, etc. Thinking a little bit more long-term, we will be comparing this flux measurement system to more traditional micromet flux measurement approaches at Duke Forest, and exploring the feasibility for deploying into existing networks. Looking at the sites that are out there, CASNet, AMON, NTN, Improve, how suitable are these sites? What does the fetch look like? If we have historical micrometeorology, can we analyze that data along with atmospheric chemistry to select some sites that might be the best candidates for these measurement systems? And then we want to develop a better idea of the labor requirements of running one of these systems so that we can get a better idea of how much training might be needed for site operators or how much of a time commitment it is beyond just the Tuesday responsibilities for AMON or NTN site operators. So we'll be working on some of those details as well. So that's where we are in terms of our development of the prototype system here at EPA. Like I said, I hope to be able to share some more quantitative results with you if you join us at the spring NADP meeting. But for now, if we have time, I'll try to address any questions or comments.
Thanks, John. Oh, go ahead.
Well, I was just going to say, while everyone is thinking up and jotting down their questions, I'll mention that another aspect of this system that we're thinking about more long-term is how we can use the conditional sampling approach for other applications. For example, maybe deploying this system and not just sampling conditionally on stability, but also wind direction to characterize fluxes during upslope or downslope conditions, or upwind, downwind of a particular source. So, and how can we use the conditional sampling to our advantage, and in other ways to characterize air surface exchange, or maybe using the denuders and filter packs to measure fluxes of things other than reactive nitrogen. So we're also thinking about the flexibility that the conditional sampling approach and the denuder filter pack sampling approach might offer for other applications.
Hey, John, this is Mike Bell. Is there a way that you could put that like a little bit higher up? So I was just like kind of thinking of deposition to like a shrub system, like looking at fluxes over vegetation versus like over a grassland and something like in Idaho?
Yeah. The European groups have deployed these systems over forests. So you can do that. Again, you have to have you would need a site where you have a tower that gets you well up above the surface, and you would, the fetch requirements for these taller measurements, require a larger upwind area where the vegetation is consistent, et cetera. But yes, in theory, you can deploy these systems over taller vegetation to measure fluxes.
Hey, John, that's very interesting. Thank you. First, a comment as to the value of an inexpensive system that can be deployed spatially is that, we've often wondered. We did some studies in the Snake River Valley near Tetons, and we wondered why the concentrations, while relatively high, were actually low relative to like what you're measuring. And so, what's the deposition flux along that Snake River Valley would be fascinating to understand the contributions to places like Tetons and Yellowstone from a nitrogen deposition standpoint. A question for you about your instrument. How quickly can you, or do you need to be able to switch from one mode to another? And then based upon that, what is the residence time, and does it matter from the inlet to the filter? And I'm wondering, if you start to switch relatively quickly, could you be leaving mass in your inlet that never gets to your filter, or gets to the filter at the wrong time, which could be uncertainty in the analysis?
Yeah, that's a good point, Brett. I think if you do sample too frequently at these low flow rates, you would run into that problem. The way that we do it is that we, at the end of every 30-minute period, we calculate the micromet parameters, and then we, based on what they are at the end of the 30-minute period, we switch the valve. So the valve is staying in a position for a period of 30 minutes or longer if the met conditions maintain consistency. So we're sampling over a minimum of 30 minutes to each channel.
Okay, I guess I had missed that, but I guess that also could introduce uncertainties, you think?
It can introduce some uncertainties if you're at a site where you're shifting in between stability conditions frequently. So if we're sampling on the unstable channel, and then our micromet is at the end of that 30-minute period telling us, all right, now we need to switch to a stable channel. When the conditions become more variable on a 30-minute by 30-minute basis, I think that can introduce some uncertainty. This approach works best when you have several hours of a consistent stability condition, as you might see here in North Carolina overnight. When the sun goes down, you shift into that stable condition, and it stays there overnight. Then you shift into the unstable category during the day, and it stays there for several hours. Or you have a day or a day and a half with a frontal passage where it's very windy, and you're staying in that neutral condition for an extended period of time. But yes, highly variable conditions, I think, do introduce some uncertainty as well.
Thank you.
Along those lines, I guess, you look like you kind of go from slightly unstable to neutral to slightly stable. And your sampling in Idaho, you said started in the fall, which you're probably mostly in relatively neutral to stable conditions.
Yeah.
Have you tried this in very unstable conditions, which you're going to see probably in Idaho in the summer, for example?
No, we haven't yet, but you're exactly right. At that particular site, we're in the neutral condition a lot of the time. It's just so windy there.
Yeah, I expect in the summer it may switch to a lot more unstable.
Yeah, we do. We have seen some periods of unstable conditions during the day, and we'll see that a lot more in places like North Carolina, where we'll be bringing the system back here in the summer and running it in a much different environment, where I think we'll be able to look at some of those things that we can't really look at in much detail at the Idaho site.
Yeah.
Duke Forest will be very different in terms of the meteorology and also the atmospheric chemistry.
Okay, thanks.
John, do you have any sense? It looks like you're measuring in all conditions. So the sum of your channels should equal the total concentration. Have you checked that?
We have not checked that. But you're right. Yes, it should. What you should have is a continuous time series of concentration. So you shouldn't. With the dead band, you're always, that in combination with the other three channels, you should always be sampling the air concentrations. We're only calculating the flux when it meets the stability conditions, so we will not have full temporal coverage of the flux itself. And that's an area of uncertainty as well, and that'll vary by site also. But because you know when you're not sampling the flux, you can then look at how much of a 2-week sampling period does our flux calculation really represent. So there's we can quantify that in terms of temporal coverage.
Any other questions?
Yeah,
go ahead.
One from Environment Canada here, and bearing in mind that it's a modeler who knows nothing about measurement systems. You know, when you're talking about your comparison to traditional flux measurement systems, what are you going to compare then? Are you going to break up these particular stability conditions and do the comparison under those stability conditions, or are you going to try to measure the total flux in both cases over time and see if you get an estimate of the total flux?
That's what we would do. So we would want to break down our hourly or half-hourly flux measurements and compare the fluxes over the same periods under which the conditional sampling system is measuring. And then we want to see, ignoring these conditions, ignoring the periods outside of these stability conditions, how important is that? How much does that bias the flux that we get when we measure it at a half-hourly basis and aggregate that up to a week? So we'd be looking at those two sources of uncertainty.
Okay, fine. Because I was trying to make I can see the value in doing the measurements under different stability conditions from the standpoint of, for example, trying to improve model parameterizations and so on. But from the standpoint of trying to measure the total flux, you know, it strikes me that you know, if you're going to have these things and they're only operating, or at least they're bidding things into these stability conditions, are you going to miss some of it? And so that final comparison, that's what I was wondering. Okay, so you are going to try seeing how the total flux compares then to when it's been subdivided into stability conditions. Okay.
That's right. And we're hoping that maybe by using both the traditional aerodynamic gradient technique and the modified Bowen ratio that we can extend that temporal coverage. So maybe there are some periods where the aerodynamic gradient approach fails because the stability corrections are too large, but the heat flux and the temperature gradient are well resolved, and we can use the Bowen ratio technique. So there will also be some comparison of those two approaches that is necessary.
Okay, thank you.
Okay, thank you, John. We appreciate your talk as always. And with that, I think we should probably move on to the next talk. Katherine Benedict with CS2 will be talking with us about the characterization of organic nitrogen in air and precipitation. And it looks like Mike is trying to transfer controls to you, and there it is. Thanks, Katie.
Okay. Yep. Okay, so today I'm going to cover the chapter from the TDep white paper on looking at organic nitrogen in air and precipitation samples. There we go. So first I wanted to start so that we're all on the same page to talk a little bit about what organic nitrogen is and why we care about it. So these are just compounds that contain both nitrogen and carbon. They can contain other atoms as well. We find them in gas, aerosol, and precipitation samples. And there are measurements. They're not very extensive, but we know that their abundance varies with time and location based on the measurements we do have. And we know that there are both biogenic and anthropogenic sources. We're really interested in organic nitrogen for a few different reasons. You know, with this group being TDep, we know that, you know, nitrogen deposition is important and there are ecosystem changes that happen. And so organic nitrogen is can be an important part of that, as we'll talk about in a few minutes. There are also other implications just generally for air quality and atmospheric chemistry mechanisms. And one particular example is oxidant cycling and the oxidizing capacity of the atmosphere, as some organic nitrogen compounds sort of come from NOx and VOC reactions, and then can be react even further or come apart due to photolysis. There are also health risks associated with some organic nitrogen compounds, and two examples are nitro PAHs and isocyanic acid. And so there's quite a few reasons to be interested, not just a deposition perspective. And so we sort of identified three main gaps in knowledge related to organic nitrogen. First is an incomplete speciation across the gas, aerosol, and precipitation phases. As we'll talk about in a few minutes, we have some measurements that are pretty well speciated in certain areas, and generally they're pretty good in the gas phase, but aren't as good in aerosol and precipitation. There's also limited spatial and temporal coverage. Generally, there are a few studies for a short period of time in a specific location they maybe last for a month or two, sometimes longer, but we just often don't have a very complete record in any one location. And part of the reason for these two knowledge gaps, 1 and 2, is that there is no standardized sampling or measurement protocol. For the gas phase, there is some more standardization, but for aerosol and the aqueous precipitation samples, different groups do different things to characterize the organic nitrogen. So what do we know? What have we observed? In terms of bulk measurements, this is just how much organic nitrogen is there. We usually measure this using the total nitrogen technique. And so we measure the total nitrogen and we subtract off the inorganic components to get the organic nitrogen. The total nitrogen can be measured by a few different techniques where we essentially oxidize all of those organic species and then measure the oxidation products sometimes, usually like NOx or NO specifically. There are quite a few measurements across the U.S. and some in Europe as well. In terms of wet deposition, we see that on average, organic nitrogen contributes 25% of the total nitrogen deposition. And then the range varies from about 3 to 33%. It's pretty similar in the aerosol phase. I think these measurements are a little bit more limited. The average is a little bit higher at 31%, and this would be just the water-soluble component. So there could be compounds that are not water-soluble in aerosol that we're not capturing with these measurement techniques. The range of the contribution in aerosol of organic nitrogen covers a similar range, about 3 to 33%. But again, these have been mainly made in North America, so there's quite a bit unknown outside, in other parts of the world. If we think more about the speciated compounds, we're going to start with gas phase. And so these are the most comprehensive when we think about the different phases that the organic nitrogen can be in. Often we have measurements of alkyl nitrates. People tend to look at fluxes and also their importance to the volatile organic carbon budget. When you make a lot of the VOC measurements, you can get alkyl nitrates as well, which is beneficial for us who are interested in the organic nitrogen. There are also measurements of proxyacyl nitrate and PAN and its homologs. This tends to be more focused on NOI budgets and ozone cycling and how these compounds because these compounds can be transported long distances, and they're pretty stable at cold temperatures. So if they get lofted higher into the atmosphere, they can go quite far. And so there are a few locations that have long multi-year records, but many places don't have a record at all. So there's quite a bit still unknown about the variability spatially of PAN. Then there are some compounds that we associate more with biomass burning that are often measured in specific studies targeting biomass burning plumes. Those include hydrogen cyanide, acetonitrile, and isocyanic acid. And then there are amines that we have some gas phase measurements of. These are not, measurements of amines in the gas phase are not as standardized as these other species that are listed above. But the ones that do exist are focused on agricultural areas. We know that there are sources in other areas, particularly urban areas, but measurements are much more limited for the gas phase. And one thing I mentioned NOI previously. NOI is a pretty popular measurement because you essentially take all of the NOZ, you subtract off NOx, and you get NOI, and that's a thermal conversion of those compounds. But it can be problematic because the compounds that make up those organic species that we're trying to quantify convert at different temperatures, and depending on that conversion temperature that your catalyst is set at, you might have different efficiencies of conversion, and maybe not all compounds convert at the same time. So comparison between different techniques or different groups making the same measurements are pretty uncertain. And in some cases, while the goal is mostly to look at oxidized organic nitrogen, usually is what we talk about when we think about NOI, people have seen that reduced organic nitrogen compounds can also be converted, even if that is not the goal because the catalyst temperature was set incorrectly. So it's something to be aware of when we consider NOI measurements. People try to look at the NOI budget and then measure the different components, like we mentioned above, PAN and alkyl nitrates, etc. And often we cannot completely recreate the NOI budget with those speciated compounds, so there's a missing organic nitrogen component. There are some potential compounds, like more complex organic nitrates and isoprene nitrates that can contribute to this missing NOI, but that could be pretty location dependent, and probably more work needs to be done to better characterize and identify what should actually be measured as an NOI, or if a focus should be on the speciation, and I think that's really where the community is going regarding NOI. If we think about the sources of organic nitrogen, we can have direct emission. A lot of times this is associated with biomass burning plumes. This can be both gas and aerosol emissions, or formation of aerosol in those plumes because they're so concentrated. And also agriculture often has specifically amine emissions. We can have direct formation in the atmosphere from chemical reactions. Aerosol organic nitrogen specifically has been observed to be associated with biological emissions in marine environments, and in continental locations, biological sources can include pollen, spores, yeast, and plant material. So there are a lot of natural sources as well. But often some of the size of some of these biological sources is larger than a lot of our traditional aerosol measurements. And that's something we need to keep in mind depending on what the goals of the measurement are. So when we think about what has been observed specifically for aerosols, there are a variety of species, but many have not been well identified. Some speciation measurements are focused on specific classes of compounds, like amines, amino acids, and urea, but other measurements focus on compound classes or functional groups because a mass spectrometer is used and there is fragmentation of the compounds, and so they can only get so much information about what is in the compound. They don't actually get the structural information, which really doesn't help us figure out where those organic nitrogen compounds are coming from. A lot of different types of organic compounds have been observed in aerosols, depending on the techniques used. Those include organonitrates and amides and nitroaromatics. And these three compound groups have pretty different characteristics, which makes it hard to identify one measurement technique that could be used to sort of examine all of them, where you would retain that structural information and better associate the organic nitrogen compounds with the sources. There is some laboratory work specifically related to organic nitrates. That's pretty interesting, where they're looking at reactions of biogenic VOCs with NOx. Historically, the work on organic nitrates has more focused on ambient concentrations, but recently it's been a lot of laboratory work. And if we think about precipitation and what we've seen for speciation, this is really the most limited set of organic nitrogen measurements. And this is due to low concentrations in many environments. The amount of precipitation that falls can really affect the concentrations that are measured, whether inorganic or organic compounds. Some groups have been successful measuring amines, 2-nitrophenol, and atrazine, for example, but the specific compound analysis is not very popular in rainwater samples because it is so difficult due to the low concentrations. Other studies, specifically used by Altieri, have done more of this mass spec type work where they identify different functional groups. And so in some of those studies, they've identified compounds that contain organic nitrogen compounds that also contain atoms like sulfur and phosphorus, which are pretty interesting. Those were in the marine rainwater samples. In New Jersey, they found reduced nitrogen functional groups, organonitrates, and nitroxy organic sulfates. And so it's a pretty complex mixture in some instances in those rainwater samples, which also can make the speciation difficult if you have to use a lot of different techniques to quantify those. And I've tried to make this summary slide to sort of summarize the measurement techniques a little bit more generally, to sort of highlight maybe the benefits and drawbacks of some of them. So we can have a bulk organic nitrogen measurement where we get how much but not what it is. And in some instances that might be sufficient, specifically if we're talking about a deposition budget. Other measurement techniques where we move more towards a speciation, where we look at something like amines, we have a limited number of compounds detected, but we are very confident we know what they are, and maybe that will help us figure out where they come from. Unless we make a bulk organic nitrogen measurement, we don't know their contribution to total organic nitrogen. And then this other method is, getting a lot of different formulas with no species-specific information. Occasionally, they can be identified depending on, how much calibration and pre-work has been done, and if there are even standards someone could buy to help, identify and quantify what there is. It might give us, a range of the different type of compounds present, but it's often really hard to quantify the species that are measured using, more of a wide net technique, I guess is what we call that. And so now I'm going to move into more of what the current state of the science is and how we make some of these measurements. So for gas phase measurements that are speciated, mass spectrometry is the main technique, using a few different types of separations. And so GCMS, gas chromatography with mass spec, we can measure alkyl nitrates and peroxyacyl nitrates. Proton transfer reaction mass spectrometry, we can get acetonitrile and hydrogen cyanide. So also from these two first ones, you can see we can't get everything at one time. So there's no instrument we can put out to measure all the things we're good at measuring in the gas phase. We can also put out a chemical ionization mass spectrometer, and this has the ability to measure both inorganic and organic species, like those listed, but it can't do them all at one time. They need different ionization sources because they have different affinities for them. There are some things you can do to maybe make some more simultaneous measurements with ion switching, but it's not easy. And so these three methods in particular are very expensive. These instruments are expensive, and it's time consuming to process all of the data. They're high time resolution, so that is good, but it takes a long time and a lot of money to run them. Sometimes you can use some of these similar techniques for the aerosol precipitation samples, but a significant sample preparation and often derivatization is involved. And so that makes it a significant drawback for many groups because it takes much longer to do these. Some people, you can use a phase transition too. You can use thermal desorption off your filter to get it to your sample to the gas phase. But often people choose other methods to try to better identify the species in aerosol and precipitation samples. So if we think about how to speciate these samples, since those other techniques don't necessarily work as well, the main technique used is liquid chromatography. And there are some compound-specific analyses for amino acid, urea, and amines in particular that we have a lot of confidence in. Separation on the top of that figure there shows an amine separation that we've developed at CSU in our lab. We can also couple liquid chromatography to electrospray ionization mass spec technique, where you separate compounds and maybe you don't know exactly what they are, but based on some of their characteristics, they get separated, and then you can fragment them, and you get a mass spectrum where you can then at least get the elemental formula, and then you can try to figure out maybe what the sources are. There are some quantitative methods for things like amino acids, heterocyclic amines, and catechol and nitrophenols, but depending on your ionization source, it can be hard to quantify these well. The Altieri paper that I mentioned before for the precipitation samples, where they got all the elemental formula, uses ultra high resolution electrospray ionization, Fourier transform ion cyclotron resonance mass spectrometry. So that's pretty fancy and expensive, but they can identify lots of different types of organic compounds. And they do see differences in aerosol and precipitation. They don't have the exact structures, but they do have the formula, so that provides at least some information that is useful. There are also different types of, an online technique that probably most of us are familiar with for aerosol speciated measurements is an aerosol mass spectrometer. One issue is there is significant fragmentation, even more than the electrospray ionization that we talked about before. And it's really hard to determine the specific compound present. You know that from some of those fragments, some of them were organic nitrogen containing, but it's really hard to recreate what they were. There's also a group from the University of York that has developed a two-dimensional gas chromatography method with mass spectrometry and nitrogen chemiluminescence. And so because they use this nitrogen chemiluminescence detection, they have improved sensitivity for their organic nitrogen detection. And the use of GC makes it more likely to be reproducible than the LC methods. And so an example of this separation is shown in this figure. We're on the x-axis, that's the first separation. You can see, there's separation across that, but then when they do the Y separation, so it's time on the X and Y axis, but it's through the second column where you see some of those clusters sort of come out and where it looked like if you only did the first separation, there would have been one compound. You can see that there were definitely 3 different ones there. As I mentioned before, when you try to do some aerosol sampling and use GC, there's a lot of sample preparation, and so that is one of the drawbacks of this method. In addition to some difficulties with the measurements themselves, there are some known issues with the sampling and collection of organic nitrogen. You know, we know that there is a lack of method testing and comparison between the methods, and we don't know how well necessarily offline and online sampling is comparable, as well as, you know, between different groups who use different techniques. And in this one study I've shown here, they saw that the comparison between offline, like filter collection, and a real-time sampling, there was a negative sampling artifact. So they were losing material off the filter as that sample was collected over a 2 to 3 day period. And so this is probably due to some volatilization of organic nitrogen from the filter, like we see for nitrate or ammonium when it's collected on the filter, but it could also be some chemical transformation, as there can be chemistry happening on the filter. There are issues with the aerosol filter sampling itself, depending on the substrate, how those samples are stored, and whether you try to, you know, capture what gases can be potentially lost. In the gas phase sampling of organic nitrogen, those challenges are primarily related to how efficient and characterizing how efficient they are, as well as if the aerosol component is removed, and then what potential sampling artifacts or phase changes you might be inducing by changing that partitioning, if that's an important part for that specific organic nitrogen compound. And then precipitation samples need to be carefully stored to reduce the possibility of contamination and composition change. There have been papers published about that. But what do we need to do moving forward to better understand organic nitrogen? Really, we need to develop and test new analytical and measurement techniques to make routine measurements or monitoring feasible. So we know how to measure total nitrogen. That's pretty easy. That technique is probably not going to change, and I think it's pretty well trusted in the community. But being able to expand the use of a total nitrogen, you know, minus the inorganic components, we need to really work on, you know, developing procedures to make sure the stability of the samples is okay, and that we limit the sampling artifacts. There's also already some monitoring infrastructure that could be taken advantage of from some existing national networks, where if we do the steps to develop a method and sample handling procedures, that it would be maybe not easy, but feasible probably to implement. Specifically for precipitation samples, we need to address issues related to low concentrations and the stability of the sample during collection as well as storage, and how to minimize the influence of biological material that can change the chemistry of this organic nitrogen while it's sitting, waiting to be collected, or after it's been collected. For filter samples, we can have volatilization of the filter, as I just mentioned. We can have chemistry on the filter, and we can also have that same influence of biological material on the filter, where the organic nitrogen is converted to inorganic by microbial activity. So if we wanted to implement some bulk organic nitrogen methods, we would need to develop methods suitable for the weekly precipitation samples so that we could leverage the current NTN infrastructure. I think part of this would be looking at the stability of organic nitrogen in both the bag type collectors and the bucket to see if there's a difference in a preferred method that would make organic nitrogen determination easier. And we would want to do this, some testing at a few different sites to cover the range in concentrations and temperatures samples experience. And while this is going on, we could consider testing a suitable preservative, targeting the preservatives that are most compatible with the current NTN list of compounds that they measure for. it doesn't seem like that's feasible, you can maybe take a separate alquat during the time of collection and add it to a smaller subset of the sample to really reduce, the preservative would reduce the biological activity, eliminate the biological activity. And then if we didn't think that any of the current methods could be modified in a way to make organic nitrogen measurements feasible, a modified collector could be deployed at some sites where the sample is refrigerated and shielded from sunlight, but still would maintain the weekly sampling schedule to reduce operator burdens. And so that was mainly for precipitation. For aerosol measurements, you know, we already have some pretty nice networks that measure aerosol chemistry, and so we could add the total nitrogen analytical method that, you know, John wrote about in this paper that I'm referencing here, to be able to and apply that to these weekly CASNet and daily Catmon samples and measure the water-soluble organic nitrogen in aerosol. There is some testing that would need to happen to look at the stability in the field, particularly for the weekly samples. So we would do a comparison of some daily and weekly samples. And then there is this issue of volatilization from the filter, but maybe we could identify some techniques to try to recapture, like we do with a nylon filter, the nitric acid is volatilized from the nitrates. And going forward, we really saw a need to increase collaboration between groups who specialize in measurements of the different phases. Often there are research groups that look just at aerosols and a little bit at maybe gases, but don't do like comprehensive measurements, specifically in the organic nitrogen arena. And so bringing together groups who look at gas phase organic nitrogen, aerosol, and precipitation organic nitrogen is pretty important, particularly to better identify the chemical mechanisms and maybe the transfer of organic nitrogen between those different phases, as well as quantifying the lifetimes and identifying which compounds or compound classes even are most important for the future studies. Which maybe help us address the variability, diurnal, seasonal, or annual, and which specific compounds or compound classes could help us. Looking at the variability would help us better identify the sources and the importance of different species, maybe at different times of year, in different processes are happening. We also, as part of this, determining which methods are best suited for organic nitrogen speciation, you know, bringing these groups together is important, but we also have a lot of resources and published work where we could use, you know, journal articles to identify the most widely used techniques that would be good candidates for the comparison study. And also this would help us identify which academic groups might be interested in collaboration. And so to really standardize these organic nitrogen measurements, particularly for the speciation in aerosol and precipitation, is important going forward so that we can have a data set that we can compare across studies and sites. Other things that we need are to expand the capabilities for gas phase organic nitrogen measurements. There, you know, are these existing networks where we have good aerosol chemistry and precipitation chemistry, that it's not too hard to imagine getting some organic nitrogen data out of with a little bit of work. But there's not really a way probably for us to do that for gas phase organic nitrogen. The measurements techniques are just too extensive at this point to, you know, put at too many different sites. So instead, it's probably more focusing on extending the capabilities of current techniques and deploying those in a strategic way. So we need to improve measurements of more of those pan-type compounds, as well as higher carbon number acyl nitrates. This could help close that NOI budget that I mentioned earlier. And we need more routine measurements of some of the amine compounds, specifically the heterocyclic ones, as well as amides. You know, I mentioned the AMS, and while that has significant fragmentation and not very good speciation because we can't tell exactly what those compounds were, we at least have some idea of the presence of organic nitrogen. But the AMS measures flow size 1 micron generally, and so we don't have an idea from the AMS, which is widely used both in time and space, which we can go back and look at the sub 1 micron sizes. So really, it would be nice to have a similar type method for the larger aerosol, which is pretty important in many locations. And once we have a standardized, some standardized methods for speciation and sample collection, all the things I've talked about, of course, we're going to make a field study and you know, look at real-time and time-integrated measurements to closely examine, you know, what really do we need and, you know, what could be implemented long-term. And this would be a chance to measure a complete organic nitrogen budget, because we could do this for the gas, aerosol, and precipitation samples. Ideally with a lot of collaborators who specialize in these specific techniques and in the different types of classes. And this would be great to have the organic nitrogen budget, but it would also probably identify priorities for future measurements, which we would want to do at the highest spatial coverage possible. And so, you know, it's always fun to go to the field, and I think with a little bit of work, you know, up front to better figure out which methods seem like they have the most potential, those are the ones we would choose to try to investigate in a study of comparisons. As part of this chapter for the white paper, we also talked a little bit about the importance of episodic events specifically related to biomass burning, which is really the most important one for organic nitrogen. We know that there's a significant contribution from biomass burning to reactive nitrogen, and a variety of nitrogen-containing compounds have been observed, particularly during laboratory studies, so controlled lab burns. These include inorganic as well as organic compounds. There are far fewer atmospheric observations of organic nitrogen from biomass burning, but there have been a few recent, and there are also some upcoming field campaigns specifically targeting biomass burning that could help address some of the knowledge gaps in this area. But I think it's important for us to consider when we are trying to develop methods to look at organic nitrogen, we do want to be able to assess how important some of these episodic events like biomass burning are. So we want to maybe identify some tracer species that could be used to look at the impact of fires on the organic nitrogen budget during fires. And the last thing I'm going to talk about here is isocyanic acid. I mentioned at the beginning that this is one of the things that has a human health impact, and the primary source is biomass burning. It has health impacts at below 1 ppb, and there have been, you know, a few events related to like industrial exposure that have been pretty significant, I think particularly in India. But because there are such essentially bad impacts to human health at low concentrations, there are potentially significant ecosystem impacts at these low concentrations as well. But there aren't very many measurements of isocyanic acid. And so to better understand, you know, the cycling fate of it, we really need to have more measurements in different environments. And I'm going to just say before I take questions that I was not very consistent about what I included for references, but most of this was taken pretty directly from the white paper, and I'm happy to point people in the direction of references if I didn't include them in this talk. But I have them all, and they're in the white paper. You can go read it, but you don't need to now.
Thank you, Katie. Are there any questions? And take yourself off mute if you are asking a question.
Hey, Katie. I guess one of your recommendations was to look at the stability of the sample, and the organic nitrogen in the sample between that collected in the bag that NADP is moving to and what they currently do by collecting it in the bucket. Have you started to look into that question? And do you have any, if so, any preliminary results?
Brett, you're the only person on this call who probably knows that I'm doing that because you're funding it. We have data. I have not really had time to dig into it and figure out if there is a difference yet. I'm hoping to have time soon. But we're doing it right now.
Okay.
Katie, this is John Walker. I have a quick question for you. Thinking about these low flow denuder measurements, what do you think is the feasibility of being able to coat the denuders with something that would collect total oxidized or total reduced nitrogen in the gas phase? Does the acidity of the coating solution just present an insurmountable problem for resolving organic nitrogen in a denuder measurement?
So I think a total measurement, using a combustion method, I think that's doable. We've sort of done that a little bit to see if it would work. We've tried, we can do filter samples, with an amine IC method, but we haven't been able to do denuders, even when we know they have probably amines on them, because the pH is just too low. It messes up the separation completely. So I don't know if there's some technology waiting to help us fill that gap. But I think if, maybe the total nitrogen is the way to go for now. But we might need to do some speciated measurements nearby to figure out how good of a job we're doing and what we're actually measuring.
Yeah. Okay, thank you.
Any other questions? Okay, I think we'll wrap it up. Thank you to Katie, and thank you to John for not only authoring the chapters in the white paper, but also participating on the seminar and being willing to present this all to us. The last time I sent out an announcement, I believe I attached the long-term schedule. We've got talks going through August of this year, and our next seminar will be March 18th. Lucky John Walker gets to talk to us again about the application of the bidirectional ammonia air surface exchange model at AMON sites. And then Tammy Thompson is also going to talk to us about the development and testing of sources, receptors, and hybrid-oriented apportionment methods. So I will be sending out an announcement of that next call, and until then, we will talk to you in March. But thanks everyone for calling in, and have a great day. We'll talk to you soon.
Thanks, Christy.
Bye. Bye.